The session is about generation of violation witnesses by under-approximation abstract interpretation. So this is work by Marco Milanese and Antoine Miné, and Marco is going to give the talk.
Okay, thank you for the introduction. So in this presentation, I would like to present some work I did in collaboration with my supervisor, Antoine Miné. And this is about a backward analysis with abstract interpretation for finding under-approximations. So this is the outline of the presentation. I want to do a brief introduction, then I will show the main contribution of our work, and then I will discuss a bit about implementation and results. So as we know, abstract interpretation is sound by construction, meaning that we always know that the abstract interpretation of a program S will always compute an over-approximation of the concrete interpretation of the same program. And unfortunately, this means that we can also have this issue of false alarms, which means that a program S may be correct with respect to some specification, but the abstract interpretation may fail to prove that this is the case. And in practice, this occurs a lot, and that is why we want to have a way to classify alarms in some way. So an approach for this would be to look for counterexamples for alarms in general, and this is what we can do, for example, with some model checking methods, also by symbol execution or incorrectness logic. Unfortunately, most of those methods, and they often are limited in terms of scalability, because, for example, they handle loops by unrolling, or methods such as symbol execution may have problems with an exploding, so a very big number of paths, and so again this can trigger some scalability issues. On the other hand, abstract interpretation can handle these issues because, for example, we handle loops by widening operators. So to show what we would like to do with this analysis, I have a short example. In this simple program, we have two variables, I and j, and an array of 3 elements. So this loop here, in this loop, at each iteration, we non-deterministically increment j or leave it unmodified, and at the end, we access the array with the with the value of j. So conventional analysis by abstract interpretation will find out that j is between 0 and 15, but and so again we have an alarm at this location here because we may overflow the array, and so we want to have our background analysis here and find out whether this is a true alarm or not. So we start with the condition that makes this a true alarm, so j between 3 and 15, and then we go backward in our program looking for preconditions that actually make this alarm a true alarm. So when we analyze the loop, we want to be sure that no matter the non-deterministic choice we take here, so whether we increment or not j, we always find some precondition that will be such that if we reach this location here, j will be in this bound. And so the output for this is that the input must be between 3 and 10, because in this case, if this is the case, no matter the non-deterministic choice here in the loop, we'll always reach this location and make j be in this interval. But I would also like to remark that an under-approximation of this interval here is also a valid precondition for us. For example, you can take 4, 6, any input in 4, 6, and still you get a condition that if it will reach this location here, j is in this interval again, so again the alarm is a true alarm. So to summarize, the kind of precondition we want to compute are sound for under-approximations rather than over-approximations like we do usually in abstract interpretation. We want them to be independent from non-determinism, meaning that no matter the non-deterministic choice you take in the program execution, we always, if you reach the alarm location, you make it fail. And we want to find those conditions by abstract interpretation. So fortunately, this analysis was already presented in some previous work by Antoine Miné, in particular in this paper about under sufficient precondition analysis. And this analysis computes a sort of abstract interpretation equivalent of the Dijkstra's weakest liberal precondition, but with non-determinism. I want just to show a bit how does this thing work. So let's assume the simple while language with only numerical variables and those three statements. So this analysis works by induction on the syntax. So if you want to, for example, analyze the program made of the composition of two subprograms, you just perform the backward analysis of the second program first, and then the first program. For if-then-else blocks, you first analyze the two blocks, the guards, and then you perform the intersection of the two results. While loops are handled by greatest fixed point instead of least fixed point. And finally, for the atomic statements that for this simple language are only assignments and guards, we have some direct formulas to compute the results. And I also want to remark that for the Boolean filtering, we have a union operator here. And we will use this later. Okay, so this work was mostly in a seminal work. And of course, it has many limitations where we want to apply it for real-world C programs. For example, there is this union operator that we have just seen. And unfortunately, it's not easy to compute the union with abstract domain because we need to have an under-approximation, so we cannot use the join operator because that will compute an over-approximation. There is no support for program inputs. I will say a bit more what do we mean with program inputs. The original work was assuming as integer semantic where you really have mathematical integers, while in C programs you have integers with a finite precision. There was no support for arrays and memory, and also there was only support for a polyhedra domain, and maybe you want to have some more powerful domains or even partitioning techniques. So there's a lot of work on doing this for this. So of course in this work we haven't tackled all those issues. We mostly focused on union, program inputs, and integer semantic. So to show what I mean by program input, I want to start with this by comparing those two very simple programs. So in the first program, we have this input command, which we assume will be getting some input value from an external user, and so in some sense, the result of this statement is we assume it to be controlled by the user, whereas the run command on the right is some non-deterministic choice embedded in a transition system, so we assume it not to be controllable by the user. So the original work was only supporting this kind of non-determinism and not the input. So in order to add support for those input statements, we extended the language and we tried to provide a semantic also for this command. So our approach is to augment the state that beforehand was just a map from variables to their corresponding values, and now we had also we had support with we had some streams that will represent the inputs from the user. And the semantic of this input command, so a stream is just an infinite sequence of integers for us, like this. And whenever we execute an input statement, we are just reading one value and putting it into the variable and moving a pointer in the stream by one. In order to have an abstraction of this, because we want to handle this we want to make this an abstract domain for this, we take a very simple case where the stream is repeating always the same value, and this is very convenient because we can reuse some conventional numerical domains and encode this stream simply as a numerical variable. Then there is the problem of union. So in the original work, it was mostly focusing on the polyhedra, and so at a certain point you need to you need to compute a union of two polyhedra like this here. So while for over approximations you can perform the join, and so there is this result here. For under approximation you can have multiple results. For example, you can take the triangle over there, but also the rectangle here. So there is in principle, there is no way to pick which of the two. And the original work was using some heuristic to guess which one of the two to use. Here we try to avoid to make these heuristic guesses, and so we relied on some powerset construction where whenever you need to compute a union, you just merge the two sets of polyhedra. Again, you can also have meet using powersets, and you can implement the transfer function as well by computing pointwise the transfer function on the powerset. And then finally, we tackled the issue of integer wrapping. For this, since we are working mainly with polyhedra, we reduced some work that was already done on this. And in particular, this paper by Simon and King presents how you can implement, how you can analyze programs with integer, like C-like integer semantic, using the polyhedra domain. And in particular, they show that everything boils down to some wrapping operator that needs to be implemented in the polyhedra domain. And what this operator does is, for example, if you have a polyhedra like this, which is spanning multiple quadrants of the space, of the state space, what this operator does is it simply cuts the polyhedron in multiple parts and brings everything to the first quadrant. So this is the result. So for our backward analysis, we want to have a backward version of this wrapping operator. And so what we can do here is take all the polyhedra in the first quadrant and put them back in all the other quadrants. So this is the result we want to get. And to pick which of those polyhedra should be actually kept for the precondition, we can rely on a forward pass that already gives us an forward invariant, so an over-approximation of the set of states that the program can actually reach, and so we already know which of those polyhedra are actually reachable. And so this is the way we can pick the correct polyhedra to keep. So all this work was implemented in a simple proof of concept analyzer consisting of roughly 10,000 of OCaml line. We tackled only numerical C programs, and we used mainly this polyhedra domain, and in particular with the powerset version of it, so in general sets of polyhedra. In addition, we tried also to generate violation witnesses, as in the form of the SVComp witnesses. So those witnesses will show a program trace that can make the task fail, essentially. And critical piece is missing in our analysis for this. In particular, we don't have any way to check termination. And so for this, we took a very simple strategy. We try to inject the inputs that we have found during our analysis in the program. We compiled it and ran it, so we simply checked with a time limit whether the program terminates or not. And finally, the shape of the witness we used is simply resembling the control flow graph of the program. In order to assess the performance of our analyzer, we extracted some tasks from the SVComp, in particular from this set of the SV benchmarks. And of course, we took incorrect tasks. So this is the result of our analysis. Oh God, I'm sorry, the analyzer name came out. So on blue line is our analyzer. On the red is CPA checker. This is the ultimate atomizer, and this is no, sorry. So this is our analyzer. This is CPA, ultimate atomizer, and this is variabs. So those are three leading tools from the SVComp, and we try to compare their result with ours. So the blue line consists of the programs that are successfully analyzed. The red line consists of the programs for which we have an unknown result. The yellow line is the timeouts, and the black line is the black bar is the programs where we didn't support all the features, so we couldn't analyze. So as you can see, our analyzer is not performing very well compared to the other analyzers, but still we have many less timeouts. And in particular, I want to stress that we have a major performance increase compared to the other analyzer because we are using those, since we are using abstract interpretation techniques, and so we can scale up more effectively. There are more benchmarks in the paper where you can also see this. So as a future work, we would like to be able to handle more features of C programs. So for example, we would like to have some way to analyze those programs consisting of arrays or structs, also dynamic memory allocations and so on. We would like to have more powerful numeric domains, such as intervals, congruences, but also packing techniques to make polyhedra more scalable. Then we would like to have also less trivial input abstractions, so not just streams that always repeat the same values, but also maybe something more advanced. And finally, we would like to have also partitioning techniques. So in conclusion, we have seen, in this talk, I present a bit about how you can compute sufficient preconditions. Then we've seen how we extending this analysis by adding support for some features that are very useful when you want to analyze C programs. And finally, we concluded with some experimental results. So with this, I would like to thank you for your attention. And
okay, thank you, Marco. So we have time for questions now. David Dijkstra.
Hi, nice talk. So you use a powerset domain for your union.
yes.
Do you bound the number of elements in your set for scalability?
Yes. So we do have a bound on number of elements, but we also have our refinement technique inside our power set. So during our analysis, and in some specific point, we try to merge or to combine the elements in the power set together. So we do have some kind of unions between polyhedra, but unlike the union that were performed using the heuristic. So again, we still need to have some heuristic to decide which parts of the polyhedra to merge, but we can do this in a later phase of the analysis, so we don't need to do it immediately, like when there is a union to compute. So this way we can keep a higher precision while still not having to keep too many elements in the power set. And if we cannot combine elements, there is always the option to drop polyhedra from the power set.
And a second question is, so as far as I understand, you have an alarm and you try to refine this alarm to understand if it is true alarm. For scalability reasons, is there a way to apply your technique on several alarms at the same time? Because
yeah, you can totally run. So our analysis works by computing preconditions for other alarms at the same time, but you can easily enable only a subset or only a specific alarm, multiple, so it's totally independent from that. But yeah, I mean, in the end, if you have multiple alarms at the same time, you don't know the precondition that you find, if they're precondition for a specific alarm or for other alarms. So that's the drawback.
Just one quick follow-up to the first question by David. Can you say a few words about how you do the merging? Like, how does this heuristic work? Like, if it is not too long to...
Okay, so there was already some work. So there was already some work on computing, on checking whether the union between polyhedra is exact or not, the join is exact or not, and we relied on that for relational polyhedra. But this doesn't prove to be sufficient when you want to have when you have integer variables, because in those cases, even if the union of the rational polyhedra is not exact, maybe the integer one is exact, and so in this case we have a special algorithm for computing still the union.
Okay, thank you.
Would your technique be useful for necessary precondition?
No, because for that you need to have over-approximation, so it...
Okay, so you think about it.
Okay. Okay.
Name?
Yeah, I was just curious about what are the reasons the other tools are better, and is the input abstraction one reason of that?
The input abstraction, sorry?
Yeah, is the input abstraction one reason of that?
No, I don't think it is. So unfortunately, the tasks from SVComp are more focused for model checkers, I would say, especially from this particular set. There are other sets where abstract interpreters can do a bit better, but for this particular set, I think it's not the best. I took these tasks because they were the simplest, like they consist of simple loops, but sometimes they contain, for example, congruencies, and it's not easy for our analysis that only supports polyhedra to handle those as well. Okay. So I think that's mainly the case, the issue.
Okay, so we will. Well, okay, we can take a last question and then move to the last talk.
So, hello. In SVComp, generating the witnesses is just half of the story. So you have a bunch of tools that actually are supposed to read those and then validate your claims. Have you tried those tools to see if they can actually validate your witnesses, showing that actually you are giving enough information for them to verify the claim?
Yes, so the success bar for our analyzer consists only of tasks that were successfully validated by certain validators. So all of those were validated.